Welcome Geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Hi everyone, today we are going to learn about matrices. Let's first look at simultaneous linear equations in its geometrical configuration. Remember that the equations can be represented in the form of a plane. So there are 5 ways where the 3 equations or 3 planes can interact and forms different types of solutions. So let us take a look at the first example where the planes meet in a unique point. So as you can see, the 3 planes intersect and they only meet at one point. We call this a unique solution. The second scenario is when the 3 planes meet in a line, or we call it forming a sheaf. So in this case, as you can see, there are an infinite number of solutions. In the third scenario, the 3 planes form a prism. As you can see, this is a triangular prism. And in this case, there is no solution. So in this fourth scenario, all 3 planes are parallel to each other. Hence, there is no solution to this case. And in this last example, 2 of the planes are parallel to each other. So again, there is no solution in this example as well. Note that in the later 3 cases, the equations are said to be inconsistent. So let us now look at the role of matrices in solving systems of linear equations. The procedure followed for solving or attempting to solve systems of linear equations in 3 unknowns can be presented more concisely in matrix form. An example follows. The following system of equations was solved above using the elimination method. So we have x plus 4y plus 2z equals to 15. That is our first equation. And the second one is 3x minus 7y plus 4z equals to 1. And the third one is 2x minus 5y plus 3z equals to 1. The equivalent steps are now represented in matrix form. Before proceeding, note that the system of equations can be represented in matrix form as you put a very big bracket here and write down all the numbers let's say we have 1, 4, 2, 3, -7, 4, 2, -5, and 3 for the rows. And then we have another matrix which are x, y, z, and equals to the answer, which is 15, 1, and 1. So the 3 by 3 matrix on the left is known as the matrix of coefficient, or coefficient matrix. The 3 by 1 matrix immediately to the left of the equal sign contains elements which represent the unknowns for which we are trying to solve, the x, y, z. And the elements of the 3 by 1 matrix to the right of the equal sign represent the constant on the right hand side of the equations 1, 2, and 3 respectively. In using the matrix approach to solving systems of equations such as those given above, we work with the augmented matrix. This is just the matrix of coefficients to which is added the 3 by 1 matrix represented the right hand side of the equations. The coefficient matrix is frequently separated from the remainder of the augmented matrix by a vertical line. The augmented matrix pertaining to our example is thus in this form. You don't have to write out x, y, z, and you just have to write out the numbers, and then you split the solution using a single line. The matrix approach to solving equations 1, 2, and 3 for the unknowns x, y, z is shown below. Multiply equation 1 by 3 and subtract from equation 2, and then multiply equation 1 by 2 and subtract from equation 3. And for the second step, you multiply equation 2 prime by 13 and subtract from equation 3 prime multiplied by 19, and you will obtain this new augmented matrix. You should check for yourself the correspondence between the augmented matrices on the right and the revised systems of equations shown when using the elimination method. The matrix operations, which are equivalent to the steps used in the elimination method, involve multiplying one row by a scalar quantity and adding this row to another row, which may also have been multiplied by a scalar. Thus, multiply equation 1 by 3 and subtract from equation 2 translate to multiply row 1 of the original augmented matrix by -3 and add to row 2. This is an example of a set of operations known as the elementary row operations, which can be used to facilitate the solution of equations represented in matrix form. The elementary row operations can be described as follows. The first one is swapping rows. The second one is the multiplication of a row by a scalar quantity. And the third one is the addition of one row to a scalar multiple of another row. Any combination of using the above operations can be used simultaneously in the process of solving equations using the matrix approach. Do not try to execute too many simultaneously. Consider again the system of equations given below, which formed a shift. We have x plus 4y plus 2z equals to 15. 3x minus 7y plus 4z equals to 1. 11x minus 13y plus 16z equals to 33. In matrix form, these equations becomes, you put in the brackets and place all the numbers in. So we have 1, 4, 2, 15, 3, negative 7, 4, 1, 11, negative 13, 16, and 33. Simplifying using the elementary row operations gives, so for the second row you have, in the first matrix, row 2 minus 3 times row 1. Whereas for the third row, we have the original matrix number 1, row 3 minus 11 times row 1. Note that the elementary row operations indicated refer to the matrix preceding, the result being placed in the matrix to which the indicated elementary row operations are adjacent. Thus, R2 minus 3R1 means multiply the first row of the original matrix by 3 and subtract it from the second row of this matrix, storing the result in a new matrix as shown. Now moving on to the second step, we only perform the operation for the third row. So the operation is row number 3 minus 3 times row number 2 in the previous matrix. Note that after the elementary row operations have been performed, the last row is a row of zeros. This will always be the case if the planes represented by the equations form a sheaf, or exactly two of the planes represented by the planes are coincident and meet the third in a line. Note further that if two planes are coincident, then one equation will be a multiple of the other. Let us now consider again the system of equations given below which formed a prism. So we have x plus 4y plus 2z equals to 15, and 3x minus 7y plus 4z equals to 1. And finally, 11x minus 13y plus 16z equals to 40. And we can now represent it in the matrix form, like this. Simplifying using the elementary row operation gives, so now the new second row is the previous matrix row 2 minus 3 times row 1. And the new third row will have the previous row 3 minus 11 row 1. And now, for the third row of the new matrix, we are going to perform R3 minus 3R2 of the previous matrix. Note here that after the elementary row operations have been performed, the last row consists of zeros in a coefficient matrix and a non-zero element on the right-hand side. This will always be the case if the planes represented by the equations form a prism, or if two of the planes are parallel. The latter case can be identified by noting that one row of the original coefficient matrix is a multiple of another. Below is an example of a system of equations representing three planes which are parallel. So we have x plus 2y plus z equals to 5, 2x plus 4y plus 6z equals to 12, and 3x plus 6y plus 9z equals to 20. And we expressed it in a matrix form. And then we will simplify it using the elementary row operation. So for the new second row, we have the previous second row minus 2 times the first row. And the new third row, we have the previous third row minus 3 times the previous first row. Note here that after the elementary row operations have been performed, the last two rows consist of zeros in the coefficient matrix and non-zero elements on the right-hand side. This will always be the case when the equations represent three parallel planes. So let us look at the summary of the results. If after applying the elementary row operation, the augmented matrix is reduced to 4 of these results. The first one is we have xxx, which represents the number on the first row, and we have 1 0 on the second row and 2 0 on the third row. Then the three planes meet in a point. The second type is you have 3x in the first row, 2x in the second row, and all zeros in the third row. So there are two cases where you can see this type of matrix. So the first one is when the three planes form a sheaf, or when two of the planes are coincident and meet the third in a line. In this third case, we have 3x on top, and we have 2x in the second row, and 3 zeros at the bottom, with 1, B3 as the number. Again, there are two kinds of scenario that you will meet this kind of matrix. So the first one is when the three planes form a prism, and the second type is two of the planes are parallel. And in the fourth scenario, there are 3x on the first row, and the second and the third row we have 3 zeros. So this represents all three planes are parallel to each other. So for case 2, the three planes form a sheaf. It only occurs when one of the planes can be written as a linear combination of the other two. And for case 2, the second one, where two of the planes are coincident and meet the third in the line, it only occurs when the equation of one plane is a multiple of the equation of one of the other two planes. And for case 3, the second one, which is the two planes are parallel, it can be identified by noting that if two planes are parallel, then the normal vector of one plane will be a multiple of the normal vector of the other plane. So for the number of solutions, in case 1, there is a unique solution. In case 2, there is an infinite number of solutions. In case 3 and case 4, there is no solution. Where there is no solution, the equations are said to be inconsistent or not consistent.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.